Hey guys, so last time we were doing the FEM simulation, and it's almost finished. It simulated almost half of it. So for the flip sim, we'll be using the previously simulated and clean mesh that we already have, and then for the final, I'll switch to the quad mesh uh, that is deformed by the wrinkly version of the simulation. So I just wanted to go back a little into the FEM and mention a few things. Previously, I was explaining how I use this expression here in order to mix two simulations. And what I forgot to say is what is this expression, what it does. So basically, the lerp expression is a linear interpolation expression which uses two parameters of any type. Basically, if you have, you can lerp quaternions, vectors, floats, integers, whatever you want. Like using a third parameter, which is acting as a bias. So in our case, we have the current position of the simulation, of the vertices in the simulation, and the rest position, which represents the vellum version of the simulation. And the mask that we're using here, it's the complement of the mask, basically 1 minus the mask, which inverts basically the values on the mask. What I did before this tutorial, this specific chapter that I'm recording right now, I changed a little bit the setup. I didn't change it in this scene, but I'm going to show what I've done so you can see the changes. Basically, I wanted to make it more procedural than previously. In case I want to change the mask here, I would prefer to simulate the FemSim without the mask baked into the simulation. So what I did, I disconnected this with the Y button like pressed. You can just drag over a line and cut it like this. So basically, I'll be connecting this directly and doing this mask operation. Copying the mask after the simulation is basically baked because I don't want to, in case I change the mask, I don't want to resimulate the whole FEM simulation. So I'm going to lower down these nodes. What will happen here is the time shift and the mask attribute transfer will happen after the simulation. So these two connections will reroute them into the attribute copy. And this is what's going to happen. But the only thing, the slowdown, there's going to be a slowdown because of the attribute transfer that's happening on each frame. And the attribute copy, well, attribute copy is much faster than attribute transfer. So, keep in mind that it's going to be a little bit slower to read. But in any case, we'll bake the whole final simulation here into another sequence. This is going to be the final geometry sequence that we'll use for the flip. But temporarily, we'll go back to this original vellum simulation for the flip. So basically what happens here, we have the wrinkles simulated. We'll bake in the rest position of the deformed original vellum deformed mesh. We'll attribute cast. We can remove the mask from here, clean up the whole thing. Maybe remove the mask also here. We'll keep the ID because we'll need the ID to transfer, to do the operation of attribute copying the mask back to the mesh after the simulation is already saved. So in case I decide to repaint the mask, I'll have the ability to do so without resimulating the FEM. So yeah, this is the final FEM setup. All right, and so yeah, the other thing I wanted to mention is, if you remember, we had this wiggly kind of tail. This specific tail was kind of wiggling around, and I suspect it was because of the extra energy inside the attachment constraint that we applied to the tail. If you remember, in the vellum solver, we had this vellum attached tail. And what I did in the end was activating it. I just modified this, the activation. So basically I activated for 10 frames from frame 11 basically until the frame 20. And I changed a few parameters here. Basically the sliding rate, it was 0.4 or 0.5, but I changed it back to 0.7. So the tail slides easier. And I increased the stiffness. It was 10 before, but I set it to 100. So what happened, I increased the sliding rate, so the tail slides more on the ground, and the stiffness is higher, so it stops that extra energy from dissipating and trying to, find its way out of the simulation. So the damping ratio wasn't enough to calm down the constraints on the tail. So this is why I gave it more freedom by increasing the sliding rate, and I increased the stiffness to just not allow it to wiggle that much, because the stiffness is higher, so the constraint doesn't really obey any of that extra energy doesn't just deform and move around because there's extra energy stored in the vertices or the tetrahedrons. This is how I like to think about it, and it always pans out as I want it to work, basically, because the logic in Vellum is a really yeah. Now we got rid of the extra energy by increasing the stiffness. I think the stiffness, this is what solved it, generally speaking. And the activation means that I'm limiting the time when the constraints are formed. It's a small chunk of time. It's like 9 frames, but it's enough for the tail to attach to the ground. Because I know what, like after the frame 10, the tails are all on the ground and I can attach them, and do not create any other constraints after the frame 20. Because our constraints creation is set to each frame, which means that they're created on each frame. So yeah, this is done. So let's go into the flip sim. I'll be using this cache that I used before. Oh yeah, we have the wiggly tail here, but it's already fixed in the next version. Let's use this mesh for now, but we'll switch to the fem mesh afterwards. So yeah, let's make a little network box here. In this lesson, we'll be just creating the preparation for the flip sim. We'll prepare the geometry and we'll create the emission attributes and so on for the flip. So now we have this guy. First thing we'll do is make a time warp, which is considered the standard workflow for these kind of simulations. We have this quad mesh because it was converted. We took the original quad mesh, and we point deformed it with the tetrahedral mesh. So I'll time warp it for the whole range. So, and I'll check interpolate between frames and uncheck use velocity with interpolating position. So what this now does is this. If you click on this button, enable playback at fractional frames, and you just start going to the next frame, you see that we switched from the frame 40 to 40.1 and nothing happens on the screen, which means that there's no data, deformation data, in between the frames. So we find some information at frame 40.5, but we don't have anything else afterwards. So once we switch to the time warp, you'll see what happens here. Once we go to the next frame, basically the next tick, you see that there's deformation happening here. So this arm starts to move in space. It doesn't matter how small it doesn't matter how small the frame change is. It could be 100th of a frame or a 10th of a frame, but there will be data, there will be deformation there. So these are subframe. This is subframe data that is going to be used by Flip, because we're going to add some substeps into the Flip solver, and it will need that subframe interpolation in order to solve properly the liquid on top of the monster. So the time warp, this is the standard workflow. The input range, well, I know there's a lot of artists that are listening right now that would prefer that the input range would be here and the output range would be lower, which makes more sense, but I don't know why it was done like this. So the input range is 1 to 300 and the output is the same. We don't want to retime it, we just want to interpolate between the frames. And we don't want to use the velocity for this, because sometimes it will use the velocity if you have it in stock as an attribute. And we have it as an attribute here. We have it as an attribute. We have it like if you switch this, we have the color, we have the normals, position, velocity, and the UVs, obviously. Let's check the UVs. Yeah, they're there. So now let's do a time shift, and we'll work on the emission attributes, which will be based on the curvature. Delete the channel, set to 1, and we'll calculate the curvature the old way. Because the new way is using the labs tool, which is curvature, labs, fast Gaussian curvature, and the measure curvature. So if you want to see what it does, let's visualize the output, and you can see that it just does stuff, but it's very kind of noisy. And the other one is a little bit better, labs, measure curvature, but it's a little bit slower, so keep in mind that. It's going to take a while to calculate, but it has convexity and concavity, so they're both baked into different colors, green and red. You can bake it into a single color, and you have different types here. Volume analysis, which is a little bit better, and we can use one of these, but I'll show you how to do the curvature calculation properly by hand. So let's make a VDB. The resolution is terrible, so let's go really low, something like this. Maybe 0002. This is enough for our curvature, and we'll make a VDB analysis. A great node that can calculate a bunch of volumes that are derived from the surface volume or distance VDB. So what we're going to use here, we'll use the curvature. So it outputs a curvature like VDB. It's going to keep the same name as the original one, which is surface here. And yeah, I'm going to also make a group, which I'll name normal select, GRP normals, let's say normals, doesn't really matter. And yeah, basically, let's apply an attribute triangle to this group. But first we're going to set the group parameters. I want to choose some points by normals, and I want to choose the normals that are looking up. The spread angle will be like, I don't know, 70 degrees. We're selecting the vertices that are that have the normals kind of pointing up, and it basically internally it calculates the dot product between this vector and the normals. It selects only the vectors. I mean the vertices whose dot product with this vector gets close to 1. So let's select this GRP normals, and let's set a parameter called femit equals 1 only for this group. So let's evaluate and see what happens here. So we have an emission attribute. If we change the parameters, you can see that there's a selection going on. Yeah, so we selected the tops here, and we are going to attribute blur this thing. Attribute blur the emit attribute. Let's add some of those substeps here. Maybe, yeah, we'll make another attribute triangle here, and I'm going to remap this emit attribute by ramp. So I'll basically override the emit attribute with a remapped emit attribute. So let's make the ramp here, and we're going to just, yeah, something like this. And maybe we'll inverse these guys. Yeah, so maybe not. We'll just leave it like this for now. But we have the control over the blur and how far it spreads. Let's keep it like this, and I'll make an attribute triangle. I'm mixing techniques here, so you can see that variations of the mixed techniques are working very well. I'm doing some attribute triangles and attribute VOPs, and they work perfectly together. Some people prefer using only Vex. I prefer to use any node that is available to me. So depending on my mood, I can use only VOPs. But yeah, let's use VOPs this time. I'm connecting the first input of the attribute VOP. I'm connecting the emit triangle that I created, and in the second we have a VDB analysis. So there's going to be some magic happening here inside the attribute VOP. We'll be sampling the volume, so you should be already familiar with the volume sampling node here. And in the file name, we'll use the second input because it's in the second input, and the sample position is going to be the P. We'll fit this guy and fit range, and we'll reverse this and make ramp parameter. Yeah, ramps is not that parameter. Let's connect it to the color first, and you already see that we're sampling the curvature from the VDB based on the position of the vertex. So each vertex is pulling the curvature that is created by the VDB analysis node. And it's pretty cool because it's already, you can see it here, and you can resample it. I mean, resample it. You can change the ramp. We'll call it ramp curvature. At ramp curvature. And yeah, let's make it a spline ramp, and we'll make it linear. And as you can see, there's a little bit of control there, but yeah, not much. So maybe we don't even need this ramp, but let's leave it like this for now. And I'll also create this. I'll import the emit attribute. So you either do the bind, which imports any attribute into your attribute VOP. So let's say emit, or you can do the import point attribute. It's pretty much, it comes to the same thing, that there's more inputs in the import point attribute. The bind will just import the attribute from the first input directly. So I'm importing the emit attribute. I'm going to ramp parameter this also. So remap it just in case. Ramp emit. And we're going to use the same spline ramp. I'm going to multiply these two together. So I'm going to take the emit parameter that I created here, as you've seen here, this mask. I'm going to blend it with the curvature. So let's see what happens here. And let's go back here, set it to linear, and uncheck the visualization. And you can see that we clipped the curvature by the normal mask. So this is not bad. We're going to emit only from the top of the creature. So on top of this, we'll add another thing. We'll add a noise layer, which will combine, which will just add some randomness and variation into the emission mask. So we're going to use a curl noise here. I'll make a vector to float, or maybe, yeah, we'll use a 4D noise. 4D noise uses position and time as an input. So the last value of each of these parameters is related to the time. So the offset of the time, the frequency of the time, you can accelerate, retime the time of your scene. I mean, the current time of your evaluation, basically, and basically override this value with an HVEC. So vector to HVEC, vector to vector 4. So basically, yeah, it's going to be called an HVEC. As you can see, the HVEC can be connected to the POS, and the color is different here. So if you disconnect this, set a 3D noise, you see the color is green, but when you set it to 4D noise, the color changes. So connect the HVEC to the POS. The vector will be the position, and the fourth value of the vector 4 will be our time. So if you want to accelerate this, you'll be able to do it here in the frequency. So yeah, we'll transform this noise into a float because we've been multiplying only floats for now. So let's say vector to float. Let's take our output vector noise vector into a float, multiply it like this. And let's set some parameters here because the vector is quite big apparently. So let's set original Perlin noise, set here 15, 15, 15, and here 0.4. So for the roughness, we'll set to 0.45 and attenuation 0.04. Maybe turbulence a little bit higher, but yeah, maybe 25, 25, 25. We're trying different values here just to see what works and what doesn't. And yeah, maybe we will fit this because I suspect there's values that go below 0. So yeah, I'm going to fit the float from the vector to float because otherwise it's going to try to fit the vector. So source minimum. Yeah, so basically it's a noise that goes, if you want to see what the noise outputs as values, let's make a bind export. Connect it here and make a debug. And it's going to be an attribute called debug that will be able to check in the spreadsheet and look what values we have here. So the minimum value is -3, maximum value is 3. So let's go here and make the fit range this 3, 3. But it's not contrasty enough for me, so I'll maybe go back to 1, 1. And yeah, it's probably not a bad idea to play around with these values. Clip some of them if you have too much liquid, but for now I'll use the -1, 1. And yeah, that's cool. That's cool for me. I'm gonna keep the mask in the color for now because this is not the render geometry; it's just the simulation geometry. So I'm basically killing the previous color that I had before, which is the inflation deflation attribute. But I'm gonna kill it by making this vol. And the other thing left here is making a viscosity attribute, because in the flip simulation I used variable viscosity for the liquid, and it requires an attribute, or I mean, you can make it if you want to vary the viscosity over the body of liquid and have different viscosities in different places of your, different regions of your liquid, you have to make an attribute like based on a noise or a mask that you painted on the geo. So let's make this. I'm using a AA flow noise, also one of my preferred noises. I'm gonna connect it to the position, but change some parameters here because this is gonna be a 1D noise, so it outputs just one float, and the frequency is gonna be 35, 45, 45. The max octaves to 3. I don't want it to be very complicated. The roughness to 1, and I'll remap this again. I'm going to make a ramp parameter. This is gonna be the ramp viscosity. Spline ramp again, and fit range. And the fit range is for outputting the viscosity values that I want. So I'm going to expose the destination minimum maximum. So the initial values are between 0 and 1, but the minimum viscosity, the maximum viscosity will be different. So I'm going to expose them outside in the VOP. And yeah, let's name them properly so we have them labeled correctly in the VOP. Visc min and visc max. That's cool. And we'll bind export this guy. Let's use the debug that we used because I don't want it to go to waste. Name this guy viscosity, and it's going to be output as an attribute. So if you want to display the viscosity, let's connect it to the color. And we don't see anything because our ramp is not. So you can see it now. Yeah, that's cool. But you can remap all of these. So let's make it catmull ram or something like this. Catmull ram. So yeah, this is going to be a ram that defines your viscosity, but the output values will be something like 3 to 7. But the color is useless now because it goes above 1, so it's going to be all white. So let's go back here, connect the fit. We're going to connect the ramp parameter to the color so we can see it. But yeah, we're going to go back to this multiply that defines the emission. And what's cool about the system is that you can always go back and remap some of this stuff, mask it more or less, expand it, blur it, add more range to this mask. It depends on you. So you can do really nice stuff. Mask more, mask less, go into the group normals and decrease this whole thing. Have less emission on top, have more emission on the bottom. It depends. Like if you do -1, you'll see that there's emission going on underneath. So yeah, you have a lot of options here. This is a good procedural system that works with any geometry. It doesn't matter what you have in the input here, it's gonna work. Well, it's gonna work only if you have some vertices in the geometry. So yeah, it's the color is based on the detail of your mesh. So if you have like a very sparse mesh, you don't have a lot of vertices, the color will be really not very clearly defined. So this kind of mesh, this is quite dense, so this is enough for emission. So I'm happy with this. I'll just maybe go here in the VOP, see what the curvature does. It doesn't really do much for me, but yeah, what we can do is see what happens here. We can even skip the fit range here, connect this guy like this, and you'll have the concavity, the opposite of the convexity, exposed here. You have much more emission. You can play around with the emission here, but if you want to replace the fit range that we removed from the system, we can flip this, and it's going to be the same kind of thing. But yeah, you can play around with it. Let's leave it like this for now, and if not, we'll switch to this variation and see if it works. And yeah, you can decrease the emission. It could be fun to try this. I don't know if it will work, but yeah, there's going to be a lot of emission here in the system. There's a lot of white areas. Yeah. So when you have creases like this in the geometry and you have some detail, it's a good thing. It's a good idea to try and calculate an attribute for the emission. So you have a lot of breakup in your liquid. I've done a few versions of the liquid for Joey at the time, but yeah, I had one where there was a lot of liquid emission from the body. I think I'll probably stay with the version where we use the convexity of the mesh. So we'll flip around this. We'll see if it works. And yeah, let's continue with this. We'll attribute blur this thing. the CD. So yeah, by 1, this is enough. And because we worked on the static mesh, you see the time shift here. We're going to copy attribute. This attribute will be copied to the live mesh, the clean mesh, and you see how fast it goes because we evaluated this. We evaluated this whole thing just once on the static mesh, and yeah, it's a really cool thing that the attribute copy is really fast. Let's also prepare the VDB from polygons. Let's copy actually this guy. We'll probably use this. You know what? We'll just shift drag this guy, or I'll drag this guy, and make a VDB. I'm gonna save it as a file with a file cache. I already created this file cache in the geo. Let's call it geocached. Cached. We're gonna save it as a sequence, and the difference between this and the other VDB where we calculated the curvature is going to be that the resolution will be the same, but I'm going to use a fill interior here and set some more exterior band voxels. So if you look at the bounding box here, if you use 3, the bounding box is like this, but once you set it to 10, it expands it. So for volume sampling, sometimes it's crucial to have more of that band actually expanding outside. So when you have really fast simulation and really twitchy, like really fast-moving objects on VDBs, sometimes this exterior band, when you set it higher, is going to save you from interpenetrations or particles that go inside the VDB. So yeah, now we're going to scatter some points on our attribute copy here. Scatter. So I prepared the VDB here only for the sake of the collisions, because the collisions between the flip and the geometry will be happening using this VDB. I'm going to save it later, but for now we'll continue with the sourcing. I will scatter some points here, like 1000 points, but I'll use the CD attribute as a density. Something like this. Now you see that we have points. I'll remove the relax iterations, just so we have really random emission here. What's missing here is probably some animation in the attribute VOP. So we can expose the offset of the curl noise. And let's go back. And we see the offset here. Let's set it to F. And let's see what happens here. You see that the F moves the noise around, but it's probably a little bit too fast. Divided by 10, it's a good starting point. Actually, the F divided by 10 is one of the values that I use the most for starting like a initial value, but we can divide it more so it goes slower. But I feel like the noise is a little bit too small for my taste, so the frequency is too much. 15, 15, 15. Maybe let's increase the attenuation, maybe decrease the frequency again, and yeah, let's see what happens if we 15 roughness, something like this, 555, 15, 15, 15, yeah. Yeah, so 4 octaves, the turbulence, and we have this offset that just travels around. Maybe actually a bigger noise, higher, like a lower frequency. Yeah, something like this. It occludes 777. Yeah, and maybe a little bit rougher than this. Higher attenuation. Yeah, let's do this for now. It moves around quite fast. Yeah, maybe the offset should be divided by 50, 2 times slower. Maybe 40. So yeah, we'll attribute blur this. You'll see the moving noise. We'll not see it during the emission, but yeah, you'll feel the difference. So one thing we'll do, because we have this geometry here, we don't want any interpenetration in the beginning, so I'm going to do a really simple normal displace. Let's use attribute vex, attribute VOP, no, attribute wrangle, attribute vex. It's getting late, so I'm getting confused a little. So we'll add the normal to the P, so it goes really crazy, but we'll multiply it by a channel. Push. And let's set the push to 0001. You'll barely see it, but you'll see it. If you go here, you see there's a space happening between the mesh and the particles. I prefer to do this just to avoid the particle penetrations. And maybe lower, maybe 0.6 here. Keep in mind that our VDB is going to be a little bit thicker. Yeah, so let's go a little bit crazier with this push. Oh yeah, so VDB is here, particles are there. So let's set it to 0001. They're going to be closer to the surface like this, closer to the collision volume basically. And yeah, what I'm going to do here is reuse these scatter points as a VDB from particle fluid. I used different techniques before, and this one I used the VDB from particles. And what this does is creates a VDB. I will set the limit refinement to 0, and we'll set the particle separation to 0001, and we'll have this volume created for us, and we'll convert the VDB. There's a lot of conversions happening, but there's a reason behind it, and you'll see why. Some people prefer to use the scatter points directly as a like a source in the pop source inside the flip, but yeah, there's some drawbacks there, so it's not perfect either. I'm going to use the convert VDB to convert it to polygons, and we have this as an emission source, and we'll do a flip source here. So the flip source goes here, and in the flip source I'm going to set a something like this, copy and paste it here, paste references, multiply by 2, or maybe divide by 2, because I want to have a lot of particles there. What am I doing? Divide by 2. Yeah. So we have a bunch of particles there. I'm going to show you this technique and the other one with the VOPs, but yeah, I know that it may be a little bit expensive because we're basically calculating a black and white area, scattering points there, making it like a volume, converting to geo, and converting it back to volume and points. But yeah, you'll see that we can do a bunch of stuff with this, and we'll attribute transfer stuff from this previously calculated point source, and we'll copy the viscosity and the V. Oh wow, I had something weird here. Yeah, pushes like this, and we're copying. It's funny, it reevaluates everything. And let's copy color and this viscosity. Oh yeah, we'll copy the V, and that's funny. The viscosity didn't go through because we copied only the color, and we want to copy the viscosity. So in the attribute transfer, we set the V and the viscosity. So now we have two attributes. Yeah. So this was the preparations for the flip, and the next lesson will be building the flip simulation and the flip DOP. And also I'll be covering another method for sourcing, because this one is, I mean, it's not perfect, but it works. Usually we'll have to bake this in, because this is quite expensive to calculate per frame. But yeah, let's check on our FEM simulation. Yeah, the FEM sim is going on nicely. As you can see, I have this twisting of the arm happening. That's funny. But there's wrinkles happening, and yeah, this is really nice. If you compare it to the original one, you'll see that you don't have any wrinkles here. Here you have wrinkling happening on the mesh. This is interesting. So yeah, let's save this guy as a flip prep. It's going to be the chapter number 9, flip prep setup. And we'll come back in the next lesson. Thanks for listening. See you in the next one.